If you don't want a dessert after this lesson is over, I haven't done my job. Do you remember the implication? We talked about this a little while ago. And another way this is known is the if-then. And the example we used was, if you clean your plate, you'll get some dessert, right? And this involved P then Q, right? If P, then Q. And that little arrow is the implication. Now, P is referred to as the assumption, while Q is the conclusion. And it had a pretty simple truth table. It wasn't an obvious truth table, but it was simple. So we had P and Q, two inputs or two propositions, and that gives us what? 4 possible combinations of falses and trues. So we got false, 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 true, true, false, and true, true. And the idea was that the only time that we were going to get a false from P implies Q is when your parent lied to you. When your parent said, yes, if you clean your plate, then you'll get dessert, and they didn't give you dessert after you cleaned your plate. So P is cleaning the plate, and Q is getting dessert. So if you cleaned your plate and didn't get dessert, that meant the implication was false. Other than that, if you didn't clean your plate and didn't get dessert, that's true. If you didn't clean your plate, but you did get dessert, that's the one that's a little confusing. That's the one that says, well, maybe your parent out of the goodness of their heart decided to give you dessert anyway. So that one is still actually considered a true. And then if you did clean your plate and you did get dessert, we've got a true there. Now, before we move on with this, I want to talk about logical equivalence. In the last lesson, we briefly discussed logical equivalence. And we said that logical equivalence was whenever you had a biconditional. In other words, the arrow went both ways. It's almost if you said if P then Q and if Q then P. And so you've got this arrow going both directions. And this is referred to as the biconditional. Now, from the biconditional, we can come up with something called a logical equivalence. And we talked about this in the last lesson. And the idea is that if you generate your truth table, and P is a compound statement, or even an a compound proposition, or even an atomic proposition, and Q is a compound proposition or an atomic proposition, and you find that you have a tautology. In other words, for every possible value of true and false for P and Q, the result of this biconditional is always true. And remember that the biconditional, what it's looking for in the truth table is equals. So if I have P, Q, and I have my false, 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 true, true, false, true, true, then the biconditional is true if they're equal, either false or true. Otherwise, if they're not equal, you get a false for that column. Now, the idea is that if you have a truth table and you've generated this column for a compound proposition P and generated another column for a compound proposition Q, if they are equal, then the biconditional is going to be true for every single case. And by the way, this is also referred to as the if and only if, right? And so if you find out that for every case P equals Q and you get a tautology, then what you have actually defined is logical equivalence, which is denoted with those 3 dashes instead of an equal sign. So let's go ahead and play around with this and see what sort of things we can develop based on the biconditional. So let's look at this truth table again. I've already written it up here a couple of times. We have P, Q, and then if P, then Q, right? And so you have false, 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 true, true, false, true, true. And then this is true, true, false, true. The only time that it is not true is whenever you have the assumption is true and the conclusion is false. Now, if I were to ask you, Could you please describe using words this truth table without drawing the truth table? Well, it might be a little bit of a challenge, but one of the things you could say is that the implication is true for every row except where P is true and Q is false. So P implies Q. That truth table is true for every single row except where P is true and Q is false. Another way of saying this is that P implies Q everywhere except when P equals T and Q equals F. Now I want you to see something here. This right here is one of our logic words, isn't it? We've got ands and ors and so forth. And so I might actually be able to write this something like P implies Q. Now remember, if and only if. And what I'm going to say is when P is true and Q is false, in other words, when P is true and not Q, but not only in those cases. Let me try that one more time. See this? We've got a single F here. If I say I want the case when P is true and Q is not true, it's going to give me a T there, a true there, and false is everywhere else. So I actually want to invert that. Let me go ahead and write that down. What I'm going to get is not P and not Q. In other words, you take P and not Q, that isolates this row, and then you invert it, you negate it with the not, and it will flip it over so you'll get all the trues in the locations that are not identified by this and statement, and a false that is identified by that and statement. Let's see if the truth table works out. So what I'm trying to prove is that P implies Q is the same thing. In other words, the logical equivalence. So what I'm going to have to do is prove that the if and only if is true for all possible combinations of P and Q, true and false for P and Q. It is equal to, equivalent to, not P and not Q. All right, so let's go ahead and do the truth table. So I've got P, Q, we've got false, 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 true, true, false, true, true. All right. Now, the first thing, let's go ahead and do this left side of the expression first. P implies Q. Well, we know that that's simply true, true, false, true. The only case where it is false is whenever you have a true assumption and a false conclusion. Now, for this portion, what I'm going to do is I first want to figure out what not Q is equal to. And so I'm just simply going to invert the Q column, and I'll get true, false, true, false. Next, what I want to do is I want to AND that with P. So I'm going to have P and not Q. And P and not Q, well, this AND says that it has to be true in both of the columns that I'm ANDing together. And these are the two columns that I'm ANDing together. So I have false, true, that's false. False, false, definitely false. True, true, there's our true. Remember, what we're looking for is to identify that line right there. And then we've got true, false, that's equal to false. Now, if we take the not of P and put parentheses around it and not Q. So you have P and not Q, and then negate that. We're going to flip this column and get true, true, false, true. Now I've kind of run out of room in my truth table here, but what I want to identify is the fact that this column right here is equal to this column. So if I have this is S and this is R, and I want to do does S if and only if R. And so maybe we do have room. Let's try. All right. So we have S if and only if R. And so what you're looking for is equality. So true, true, that's true. True, true, that's true. False, false, that's true. True, true, that's true. And so this tautology here, right there, says that this is equivalent, logically equivalent to this, and we've proven this assumption right there. But in the last lesson, we talked about De Morgan's theorem. And if you remember, De Morgan's theorem said the knot of P and Q, I can actually, it is logically equivalent to, if I distribute that negation to P and Q, so I have not P and not Q, and change the operation to an or, then these two are equivalent. Well, right here, I've got the negation of something being anded. So I wonder if P implies Q is logically equivalent to, well, I'll distribute the not to the P, and when I distribute the not to the not Q, that actually can't, the two negations cancel each other out, and that just becomes Q, and then the and becomes an or. Is this true? Well, let's see. Let's go ahead and create our truth table again. Told you you're going to want some dessert after this is over. P, Q. False, 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 true, true, false, true, true. Now, first of all, let's just go ahead and put P implies Q, and that was true, true, false, true, right? Now what we need to do is figure out what not P is equal to. Well, not P is just the inverse of this column right here. So all the falses become trues, all the trues become falses. And now what we're looking for is the or of this column with this column. So you have false ORed with true, that's true. True ORed with true, that's true. False ORed with false, that's that unique case that an or outputs a false. And then we have true ORed with false, and that's true. And look, those two columns still the same. So we've got what we are looking at here is this logical equivalence. So I forgot to write down, label this column. This was the not P or Q column, right? And now if I take this and say that this is S and this is R, does S if and only if R? Well, we've got true, true, that's true, 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 that's true, false, false, that's true, 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 that's true. And the tautology there for that if and only if says we have logical equivalence. Okay, are you tired of the implication yet? Well, let's go back to dessert. If you clean your plate, then you get dessert. P, clean the plate, then Q, get the dessert, right? Well, is there another way of saying this? For example, can you say that if you got dessert, you cleaned your plate? Let's look at that truth table again. So we've got P, Q, false, 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 true, true, false, true, true. P implies Q, that's true, true, false, true. Now, that statement that I just made, if you got dessert, you cleaned your plate. Not necessarily true. Remember that case where your parent, just out of the goodness of their heart, gave you dessert even though you didn't clean the plate? That resulted in a true, right? So what we're saying is if you got dessert, then you cleaned your plate, no, it doesn't work. So that's not quite right. But it turns out there is a way that we can swap things around that does work. And the way that works is, and we'll just say P implies Q is the same, or we'll show that it's logically equivalent to not Q implies not P. In other words, going back to the dessert, if you didn't get dessert, then you didn't clean your plate. That may still not feel right, but in fact it is true. Let's go ahead and prove this. We've got not P, not Q. Let's go ahead and make columns for that. So we're just going to flip P, true, true, false, false. We're going to flip Q, true, false, true, false. All right. Now, what we're looking for is Q, and I probably should have swapped those columns so that they were going the right direction. But what I've got is Q bar, or Q not Q, implies not P. So not Q implies not P. And remember, the only time that we get a false is if you have a true for the assumption and a false for the conclusion. And the place that that occurs is right here. So you've got a true implying false, and that is false. You've got true, true, that's true. False implies true, that was still okay. False implies false, that was still okay. And then if we take this last column and say P implies Q if and only if not Q implies not P. And so we've got true, true, that's equal, true, true, that's equal, false, false, that's equal, true, true, that's equal. We have our tautology, which means this is logically equivalent. Now, what this is called is actually the contrapositive. All right? It's even got a name, right? And so the contrapositive is that not Q implies not P. Let's do one more proof, and this is not necessarily going to use the implies. You're probably pretty happy to hear that, right? But it is going to use the implies. Sorry. What I'm going to do is I'm going to talk about the transitive property. Now, you've probably seen the transitive property in math. A equals B and B equals C implies A equals C, right? Well, let's see if the transitive property also works with the implies. For example, what I could do is P implies Q and Q implies R, then P implies R. Well, let's see if that works here. And what we've got is, now we have P, Q, and R. So let's see, there are 8 combinations this time. So we have false, 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 true, 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 true for P, and then false, false, true, true, false, false, true, true for Q, and then alternating false, true back and forth for R. All right. Now let's look at this first thing. So P implies Q. And remember what that's going to do is anytime the assumption P is true but Q is false, that's going to be our false. Other than that, all other rows of this truth table are going to be true. Now, Q implies R. We're going to do a similar process. Wherever Q is true and R is false, we're going to have a false. So true, false, that's going to happen in the 3rd and 7th row. Everywhere else, there's going to be a true. Now, the question is then P, and this is going to say if, so what we're going to have is P implies Q and Q implies R implies P implies R. Wow. What is that going to look like? Well, first of all, let's take the and of these two. So the and, we have true, true, false, true, false, 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 true. That's kind of ugly, isn't it? So what we've got is anytime both P implies Q and Q implies R is true, then we are going to have a true in this column. So this column right here is just for this portion here. P implies Q and Q implies R. So I guess what I should probably do is that, and we'll just put a little S here and say S implies P implies R. Well, let's figure out what P implies R is. P implies R. So P implies R. We're looking at when P is true and R is false. So we're going to have a false on the 5th row and on the 7th row, trues everywhere else. And so now what we can say is, got a little messy, didn't it? This is S, and we'll do this as T. And so what we're looking at, holy frijoles, S implies T. So what does that truth table look like? Well, what you're looking at is P implies Q and Q implies R, then P implies R. And so we have down here that this is P implies Q, this is Q implies R, and this is both of those being true. And then on the conclusion side, we have P implies R, which I'm setting equal to that compound proposition T. That's equal to true and false based on the P implies R. So now what I'm going to do is S implies T. So we have T, T, that's true. True, true, that's true. False, true, that's true. Remember, the only thing that we can have is whenever a true implies false. True, true, that's true. False, false, that's true. False, true, that's true. False, false, that's true. True, true, that's true. And it looks like what we've done is we have proven this statement right here. In other words, the implies is transitive. We can see that by seeing that there is no time when P implies Q and Q implies R is true that P implies R is false. There's no time is there that negative case. All right? All right, one more proof, one more truth table regarding implies. Let's try this. P implies Q and, remember this can be done with the little caret, right? And Q implies P. So we've got those two implies, right? And we'll just simply say that is equivalent to P if and only if Q. All right? Phew. All right, now our truth table is going to be a little bit simpler this time. And we've got PQ, so that's false, 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 true, true, false, true, true. P implies Q. We've done this so many times, you should know it's just true, true, false, true. The only case being true implying false. That gives you a false. And then we have Q implies P. So we've got this Q column implying the first column, P. And the only time that that is false is whenever you have true implies false in the second row. Other than that, all the rows are true. Now, when you AND these two columns together, when you AND this P implies Q column with the Q implies P column, so this is P implies Q and Q implies P, you get true and true is true, true and false is false, false and true is false, and true is true. All right? Now, what does the truth table for the if and only if look like? P if and only if Q. Remember that that's looking for equality. So false equals false, that's true. False does not equal true, that's false. True does not equal false, that's false. True equals true, that's true. All right? And now what we're looking at is this, in other words, this column right here, is that equal to this column? And whenever you do, well, in fact, we'll just say that this is S and this is R. So S if and only if R, you get equal, true, equal, true, equal, true, equal, true. That tautology says that we have a logical equivalence. Sorry, that was a lot of truth tables regarding the implies operation. But as you can see, we can prove a lot of things with these truth tables.